Hi everyone, and welcome back to the lab. In this video I'll be synthesizing hexachloroethane by chlorinating the tetrachloroethylene that I isolated in a previous video. This proceeds through a simple electrophilic addition of a halogen across a double bond, which you can look up pretty much anywhere. The mechanisms are all over the internet, so I'm not going to get into explaining it here. However, the caveat is that this molecule is already highly chlorinated, so it resists further chlorination, simply because the chlorines are not attracted to each other. So anyway, in fact, they repel each other, which gives this compound some interesting properties, which we'll get into in a minute. Anyway, so to facilitate this reaction, we can either pressurize the chlorine over the tetrachloroethylene and get it really hot to form the hexachloroethane, or we can use a catalyst to reduce the activation energy needed for the reaction. And in this case, strong Lewis acid catalysts happen to work very well for this reaction for reasons that will become evident if you go and read about the mechanism. So I happen to have a strong Lewis acid catalyst that is ferric chloride. So anhydrous ferric chloride will be the catalyst here. We'll simply get some tetrachloroethylene under reflux with ferric chloride, bubble chlorine through it, and we should get a decent yield of hexachloroethane. Purifying the hexachloroethane that's formed is going to be one of the major interesting points in the synthesis, because it tends to sublime very readily at room temperature. So we'll have to, rather than distill it, do a purification by sublimation, because it can't really be distilled. It'll all sublime by the time it gets to its melting temperature. It's interesting that way. So we'll explore those properties as well. Anyway, let's get to the lab and get it started. I've gone ahead and set up the apparatus for this. It's in two major parts basically. We've got a chlorine generator on this side, and then on this side is the reaction vessel itself. You can see here it's a heated vessel. I've got it in my mantle on a jack. The jack is, of course, so I can reduce the heat just in case something goes wrong. It's easy to just lower the mantle out of the way. Anyway, the tetrachloroethylene will be boiling in this flask and refluxing in this condenser here, and then we'll bubble chlorine into this using this glass tube which runs to the bottom of that flask there. The chlorine is supplied by standard chlorine generator, which is a pressure equalizing addition funnel, and in this case a 500 milliliter round bottom flask. This will contain 68% calcium hypochlorite pool shock. This will contain hardware store grade muriatic acid or hydrochloric acid. And this will be this is a drying tube. It'll be full of calcium chloride, which has been previously baked in the oven. And anyway, so the chloride will be generated here. It travels up through the sidearm and then into the head, and then over here it gets dried by the drying tube and then bubbled through the reaction. And then the waste gas at the top of the condenser gets routed out to the bottom, or to the back of the hood. And I live in the middle of nowhere, so it's not really going to bother anybody. Otherwise, you might want to set up a scrubber for any chlorine that happens to bypass the reaction. Anyway, let's go ahead and fill this with the required reactants. Alright, I'm going to start by loading the chlorine generator with 244 grams of 31% hardware store grade hydrochloric acid. And just use a funnel to get that at the top. And of course, always put your acid covered glassware into the sink. That way you don't have an accident with it later, not realizing that the stuff that's in it is not water. In the bottom of the generator, I'm going to place 105 grams of 68% calcium hypochlorite. This is just a commercial pool shock. Got it right here. Comes in sort of white, dusty granules. I will now pack the drying tube with calcium chloride, first putting a small piece of cotton down the board of the tube to keep the calcium chloride from falling into this hose here. Just like that. I think that's sufficient. Yep. A little less. Another small piece of cotton, and there's the drying tube. And I'll place the drying tube up on top of the chlorine generator. I have now measured out 83 grams of the tetrachloroethylene that we made in the previous video, rather isolated in the previous video. And I'm just going to remove the chlorine delivery tube here and pour it into this flask. To the same flask, I'm also going to add a few boiling chips, just a pair of broken pieces of ceramic to prevent bumping. and also a scoop, just a little bit, probably less than a gram, of anhydrous ferric chloride, which looks like this. It's these dark black sort of crystals. I'm just gonna probably about that much should do it. It's only catalytic after all. Alright, I've replaced the chlorine delivery tube, which you can see is down there at the bottom in the center of the flask, and all that needs to be done now is to get the condenser water going, which I am going to do right now. Just like that, a little bit slower. That should be sufficient, and we'll crank up the heat, and as soon as this is refluxing, we can start to bubble chlorine through it. Alright, as you can see, the tetrachloroethylene catalyst mixture is boiling now. The vapor front is just now climbing into the condenser, which means that it is at the correct temperature to perform the reaction with chlorine. So I can begin the chlorine flow by operating the stopcock on the chlorine generator. Alright, we're about halfway through the chlorination now. You can tell by the level of the HCl in the addition funnel there. Half our chlorine generator is left. The drying tube is doing just fine. Surprisingly, the liquid level in this flask is going down, and that's a bad sign because it means we're losing it somewhere. I don't know if it's the high vapor pressure of hexachloroethane, or maybe the chlorine that's bypassing this is taking some tetrachloroethylene with it, and I assume it's probably a combination of both. I did end up setting up a chlorine scrubber, as you can see back there, that giant Erlenmeyer. It's full of a 10% solution of household ammonia, which is just scrubbing the chlorine really quick, making ammonium chloride, of course. I did that because a whole lot of chlorine was bypassing this head here and was ending up outside. I could start to smell it in my kitchen, so I was like, well, I should probably start scrubbing that. For most reactions, of course, the chlorine is mostly absorbed by the reaction, so you don't get nearly that kind of a release. So I had second thoughts and set the generator, and now everything is fine. A good sign, though, is that there are what appears to be some crystals adhering to the glass up here, and I think that to be hexachloroethane, so that's for whatever that's worth. Anyway, I'm just going to continue running all the chlorine through this, and then we can hopefully separate some product out of what remains. Alright, well, the chlorination has been going for about 3.5 hours now, and you can see that all the reagents have been expended. The chlorine generator is done. It's just some residual chlorine being formed now, and then there's some gas left in the apparatus. Drying tube worked phenomenally. There's no liquid or anything in it, so it's not nearing its capacity or anything, which is a good sign. And you can also see at the head here, there's some deposits of solids, which is a good sign as well, because that is probably hexachloroethane. You can see that this joint is covered with some sort of solid material. The boiling point of this seemed also to slowly increase throughout the reaction, which is another good sign. So I'm just, I turned the heat off, I'm just going to let that slowly cool off, and then we can work on working on the products. As this cools, I should also mention that I removed the tube from the chlorine absorption trap because I do not have a suckback trap in between the two, and as this cools off, there's a high probability that that liquid would get sucked back through the tube and end up in the apparatus, which would not be good. So I've done that as well. So I'm going to let it cool now. I've now cleaned up the chlorine generator, and this has been allowed to sit and come to room temperature, and now we can detect whether there is any hexachloroethane in this or not. And I'm pretty sure we were reasonably successful because of the solids that are deposited on this joint up here, which is difficult to get apart now after the solvent has dried out. So I'm pretty sure this is a solution of hexachloroethane in tetrachloroethylene. And we can check that because there are differences in volatility. I've got a clean watch glass here, and what I'm going to do is take the stopper off and get a small portion of this liquid in here, and I'll drop it on a watch glass. Then we can slowly fan it until it dries. So you can see the crystals of hexachloroethylene that formed on the watch glass when the tetrachloroethylene evaporated. So we can check to verify that this is in fact hexachloroethane by checking to see whether it evaporates as a solid or sublimes rather than melts when heated. And we can try and resublime it if we have a larger watch glass. So I'm going to take the two watch glasses and put them together, make a watch glass sandwich, and then I'm going to heat the one with the crystals on it with a heat gun and see if we can get a deposit on the top surface. You can solid is now slowly disappearing. You can see the solid is gone, and there should be a very thin layer of crystals on the top of this other watch glass. So, carefully open this up, and I can see them, but I'm not sure if the camera can. There is a thin film of glittery crystals all over the top of this. Very, very hard to see, but there you can see there's a little ring of crystals right there on the edge of the watch glass, sort of. Anyway, so we were successful at producing hexachloroethane, and now it's just a matter of getting it out of this solvent. So we'll be working this up shortly. Something else is that even though the solution is fairly dark, you can sort of see that there are crystals forming right around the edges of the container, and that is contaminated with ferric chloride, but it is in fact hexachloroethane. Alright, so I've set up for simple distillation. I'm now going to remove the excess tetrachloroethylene from the hexachloroethane. See, the mixture is right in there. That's the reaction flask. It's got the ferric chloride contamination. So the plan is now to just gently distill off the tetrachloroethylene into this 100 milliliter receiving flask, leaving behind the ferric chloride and the hexachloroethane, which I can then purify by sublimation. Alright, the vapors have reached the still head. You can see I'm collecting distillate now. It's a little bit green because there's some dissolved chlorine, but that was removed first, so I'm not very concerned about that. My main concern, however, is that the vapor pressures of these two compounds, the hexachloroethane and the tetrachloroethylene, are fairly similar at higher temperatures and much different at room temperature. So the watch glass method, where I evaporated the tetrachloroethylene, works rather well. However, this method may not work as well. So I'm basically just going to have to take some samples and make sure that I'm getting mostly tetrachloroethylene and not a whole lot of the hexachloroethane coming over, and just monitor this. And when this gets down pretty low, I'm going to take it off the heat. Now, if this proves to not work, another method that I can use is essentially what I did with the watch glass, but just on a much larger scale, where I'd remove this stopper and I'd introduce a gas delivery tube, much like I did with the chlorine, except I'd bubble air through this while it's only slightly warm, and that would basically evaporate all the tetrachloroethylene off at a very high rate. So I wouldn't be here all day, and we'd be left with the crystalline product. However, this method is much faster if it works. So basically I'm just going to have to do this first and watch it like a hawk and make sure that this can be done correctly. So anyway, alright, I'm starting to get some crystallization in the still head, and the rate has slowed down to a crawl, so I'm going to go ahead and turn the heat off. I'm assuming what's left in there is mostly the hexachloroethane. Alright, this has cooled down a little bit, and I'm now going to swap out the still head for this. This is called the cold finger condenser, and you can see it's just it's almost like a test tube that's water cooled. Water's on the inside, of course. You just run water through this, and this surface here gets cold. And so you stick this on the flask, and what happens is the hexachloroethylene, which you can see, or sorry, the hexachloroethane, which you can see already crystallizing in that flask there, will sublime onto the cold finger in pretty high purity, and then we can pull the cold finger out of the flask and simply scrape it off into our collection container. Alright, so I'm going to begin to gently heat this flask, and remember, you should never heat a closed system, and this, in fact, is a closed system, so you have to have some sort of means of pressure release, like a stopper that might blow out or something. Theoretically, no pressure will be generated because whatever vapor pressure is generated by the liquid or solid inside will be mitigated by its condensation on the cold finger in there. However, in practice, this isn't always the case, so you must always have, like I said, a means of pressure release. So I'm basically just going to leave this on some very gentle heat for about an hour or so, and soon we should have all of the the hexachloroethane condensed on that cold finger. You can actually see the sublimation in action as a snow of fine white crystals falling around the cold finger. And as you can see, the cold finger has some white deposits on it, and that is exactly how it is supposed to function. And eventually, after a few minutes to an hour or so, there'll be enough on there that we can pull that out and collect it. You'll also know that the cold finger is sitting in the solution, but just barely. It's just barely touching the tip of that solution, and of course that's going to introduce some impurities, so ideally you wouldn't have your cold finger touching the solution, but unfortunately the size of the flask didn't permit that. This cold finger is meant for a 250 ml flask, but apparently this two-neck was designed slightly differently, and the liquid level isn't very conducive to that, so here we'll just have to work around it. Alright, it's been about half an hour, and you can see that the cold finger is completely covered with crystals, and that's good. But unfortunately, because the tip was touching, the crystals sort of wicked up that solution and contaminated the vast majority of them. So that is unfortunate, but recoverable. So what I'm going to do is take the cold finger out with the crystals on it and just scrape the crystals into this funnel, and they'll land in this bigger flask. And then I can go ahead and swap the bigger flask for the smaller flask after I've recovered everything from here, and then we can repeat the sublimation process, but instead we've got much more room for the cold finger and a much better way to take a look at what's going on. So I think it'll be better that way. Alright, just take this out. Carefully move it over. Scrape the crystals in. Put that back in. There's some of our crude hexachloroethane. Alright, it's time to scrape batch number 2. Alright, the flask is now getting down to dryness, and I'm just knocking the rest off the walls with this heat gun. I'm just heating up the walls to make it unfavorable for the hexachloroethane to stick there, and I would prefer to stick on the cold finger instead, and then we can harvest it. But I think this is going to be the last harvest. Alright, so we've successfully completed one round of purification by sublimation on this hexachloroethane. Now you can see here the ferric chloride is left in the bottom of the flask, and it does actually sublime itself, so just at a much higher temperature. So you'll never actually get the hexachloroethane completely pure using just sublimation. However, I just wanted to get it out of there pretty quickly so I could use it for other things. But anyway, if you wanted to get it completely pure by sublimation, you'd wash it with acid and things like that, which would remove the ferric chloride, water, acid, and then do a sublimation from the iron oxide that was left over. But I don't really have time for that, considering I was trying to demonstrate a quick reaction here, and this stuff is quite impure. So anyway, you can see this is the reasonably pure hexachloroethane. The reaction did in fact work. I've got a decent, I guess I can't say decent yield, this is like 20 grams, so the yield is pretty low. But I did get some, and it's definitely a measurable amount, so I call that a victory. I was going to make a smoke bomb with it, but then decided against it because the reason smoke bombs made with this stuff was phased out a long time ago is because it's a persistent groundwater pollutant. And since I live in an area that's sort of rural, there's lots of wells, and I don't want to contaminate anybody's well, including my own, with hexachloroethane. So that's kind of a bad idea. Also, the burning of hexachloroethane in those smoke bombs was known to produce many carcinogens, many toxins, including phosgene and things like that. So it's just not a good idea. But I can, however, explain the chemistry behind it. This reaction here is a typical representation of a common military smoke mixture containing hexachloroethane. And the reason that they used hexachloroethane is because it had such a high chlorine content by weight, and it was a stable solid at room temperature. The hexachloroethane would react with zinc to form zinc chloride, and then carbon monoxide or carbon dioxide with some of the other oxidizers that were provided to form small droplets of zinc chloride. And the reason that was important is because zinc chloride is extremely hygroscopic. So if you had a small droplet of molten zinc chloride, it would pick up water from the air as it was floating through the air as smoke, and the droplet would get bigger and bigger, and those larger droplets basically made a whole lot more smoke by weight than anything else, than say if you were making smoke with carbon particles or zinc oxide. The zinc oxide was important, and the formation of zinc oxide using the chlorate in zinc, because zinc oxide is highly opaque to a lot of wavelengths of light, including a lot of stuff in the UV and IR range, and that allowed the smoke to conceal tanks and other equipment with basically infrared-proof smoke. So that's why that stuff was added in general. But anyway, the hexachloroethane was then banned and phased out because of a number of poisonings of people inhaling the smoke that was made by this stuff, because its partial decomposition products include things like carbon monoxide and phosgene, both of which are incredibly toxic. And further, the hexachloroethane is a persistent groundwater pollutant, and if dumped outside, will eventually end up in aquifers and in your well. So here's the hexachloroethane that I made today, and I was originally going to make a smoke bomb with it, but upon learning about its environmental persistence and toxicity, I decided against it. I might save purification of this for a rainy day, considering I don't really have a use for this anymore. Some experimental notes in the future, if you're going to attempt this reaction, I would recommend bubbling the chlorine over a much longer period of time. You could probably get a much better yield if instead of 3.5 hours bubbling chlorine, you went for something more like 6 or 7 hours. But for a first try, this was not a bad yield. Also, using like 1.5 molar excess of chlorine or something like that would probably help a lot as well. Anyway, this isn't bad for the first try, and so I'm going to kind of leave it here. If you like this video, please press the like button. If you'd like to subscribe and see more of these videos, please press the subscribe button. I have a Patreon account, so if you'd like to donate $1 or something to help me continue to make these videos, I'll put the link in the description. And as always, thanks very much for watching.